so many people to come. So I'm going to talk about game programming. There's a repository online. If you have Linux, you should be able to at least, well, compile the examples if you have Linux. If you have Mac, it depends on whether you have SDL working or not, but at least you should be able to follow the code and see what's going on. I'll show you the address in a minute. So I have a company called Kira Studios, and we focus on game programming in Haskell or in at least functional languages, mostly Haskell. We also do user interface programming and desktop stuff, but mostly it's just games. And yeah, oh, sorry, yeah, I just have to shout louder. It's fine. So you may be wondering why do game programming in Haskell at all? And I think it's not that, usually people sell Haskell like it has so many benefits and it's going to save your life if you want to code. It's going to make your code so short and so amazing and whatnot. And I think it's actually the other way around. We need to do game programming. Game programming is so demanding in all respects that it's the ultimate test. If we pass it, then Haskell is ready for mainstream in all possible senses of the word. And if we don't, then maybe we're, in this safe haven where we can believe whatever we want, but it's not really true. So we just have to do it. We just have to go into game programming and write something that takes, I don't know, millions of pounds or thousands of pounds, and it's really complex. It has so many parts, physics and assets, and so many different elements, and then get a 15-year-old to judge it for us. And if this is your reaction, I don't blame you. I mean, I would too, right? So my goal during the first hour is that you understand that we already have the basic parts that we need to write a game in Haskell. They're already there. There's nothing special about them. They come from the imperative land. So you can use all the imperative documentation to know how they work. And you can get started today. You don't need to have any special knowledge to get this working. It's all very basic. So the first part is going to be, well, that imperative programming. And I'll cover a bit of multimedia, a bit of interacting with other hardware, and then we'll talk about physics. And in the second part, I'll talk about higher level concepts and abstractions like functional reactive programming and the kind of problems that we find as we build larger and larger games. So let me see. SDL, how many of you have heard of SDL? Hands up? Yeah? Okay, so SDL is a library that gives you abstractions to work with multimedia. It gives you, for instance, ways to load textures and paint them on the screen, and it does graphics acceleration for you already. It does audio as well, so you can load a WAV file and play it. Input handling, it detects when different keys and different events take place, and then it reports them to you. And you also have networking threads. I don't usually use that, but you also have ways to work with that. And it's cross-platform, so once you get it running, it's supposed to work on every platform. Once it runs on Linux or Windows, it just runs everywhere. There's two versions of SDL. For quick tests, I just use SDL1 because it just works easily. In Haskell, there's two bindings for SDL2. The old one, which is what I use, and the new one, which is maintained a lot better, but I haven't been able to compile that for Android, so I still use the old bindings. It's up to you which one to use. I think just in a few months, everyone will be using the newer version. So what it looks like is, let me see, where are we? I have a few screens open already. Let me see. Yeah, I think this is it. So, oh, I forgot to mention, this is the repository. It's Haskell game programming on GitHub by Kira Studios. And it contains documentation. Many of the examples that I'm going to show are here in tutorials. It has Yampa examples, hardware, how to interact with Kinect and Wiimote, how to do SDL1, audio, drawings, whatever. there's also tons of documentation here, and I'm adding more every day. So there's a lot of things that I covered already. So how graphics works in SDL1 is that it works like a collage. You know, you have different surfaces, and then you start putting them on top of one another. And you can draw on those surfaces. But essentially, it's just like a piece of paper. You draw on it, and then you paste it on some other surface, and then you draw on that if you want, and then you paste it on another and whatnot. And the way you get something like this running on Haskell, in Haskell, is trivial, actually. Tutorials, SDL, SDL1, let's say, for instance, this is the first example, right? Which just initialize the library, create a surface or a window. Or depends. It really depends on the platform how this is realized. But you create a surface to paint on it, and then you just fill the whole surface with a color, and then you just have drawn a window. This is called the green screen. I call this a green screen just because it was green. I don't know if you ever read that blog post in which I talked about the green screen of Haskell. I had a green screen running on Android, and for me it was amazing because it was an Android, but it was just a green screen. That's where it came from. So this is how it works. You just get the surface, paint on it, and then flip it or show it on the screen. And that's it. That's all the magic. How many of you cannot read this, cannot really understand what's going on here? This is just standard Haskell. Please. I think it has to do with how you translate different colors into the actual. So you may have a different. Is it called bit depth? You know yeah. So you may have alpha transparencies or not, and this is kind of like a way of translating colors as you would represent them in a standard way into what the surface actually supports, right? So every time you want to encode a color, you just do something like this. You get the pixel format for that surface, and then you map a color in red, green, blue into whatever that surface supports. But that's it. One important thing here is that there's a lot of codes that are monadic, and I decided to introduce SDL instead of a purely functional graphics library exactly for this reason. Because if you try to write a game, there's a lot of, at some point, if you try to add images and complexity, you're going to have to use I/O. If you use a purely functional library, then the initial example will work fine. And when you try to do something real and sell it, then you see that you have to use all this I/O all over the place, and it impacts the architecture of your application. If we start doing this from the very beginning, then we know where the impact really is. So, any questions so far? No? Okay, simple enough. So I'm going to show you, for instance, how we load a surface from a tutorial, SEL, I think drawings. Yeah, okay. SEL graphics example 1. Okay. So this is, for example, just a ball that follows the mouse, right? It's pretty simple. And the way this is going to work is that we're going to divide it in two parts, actually. One of them is going to be drawing the ball. I'm going to explain that first, and then how to detect input and draw the ball in the exact position. Let me see if I have this. SL1. Oh. Yeah. So this is an example of how you draw, or what you can draw in SEL. You have different primitives to draw lines and circles and squares, filled or not filled, aliased or not aliased, and to copy bitmaps on the screen. Right? And the code for this is tutorial STL, STL1. I think it was drawings, yeah, shapes. So let's start here. So far, this is just, forget about this. Okay, this is very similar to what we did before. We clear the screen in white in this case instead of green, but essentially this is the same. This is just clearing the screen, and forget about those parts for now. So this is how it works. You just draw a line on the surface from this pixel to that pixel. I think this is the width of the line, and then this is the color. There's a problem with STL bindings is that in some cases you have to pass coordinates using, for instance, int16, and other bindings people have actually worked a bit more on them, and you can pass just ints. So you will see that sometimes we're just using from integer all over the place, or we're rounding things, and it's just because some bindings are more advanced than others. Some libraries in STL, like the graphics library, less people have worked on it. But as you can see, this is really, really simple. It's just draw a line from here to there. Vertical lines as well, rectangles as well, circles as well. So there's nothing magical going on, right? Of course, the interface looks crappy, but there's nothing magical going on. If you want to draw a picture, for instance, like a bitmap, like we were doing before, Gioconda. Yeah. So I think I have a better example of how to load a surface here. Let me see if I, yeah. So this is an example of how you load a file, I don't know, a PNG file, and then render it on the screen. And if you remember, I talked about having a collage, like having different surfaces and putting them on top of one another. Well, where is it? Yeah, you load the file in a surface, you get the size of the surface, and then you just blit it. You just put it on top. You just paint it on top on specific coordinates. That's it. That's all the magic. So far we know how to clear a screen, how to create a video surface, how to draw lines, how to load PNG files and paint them on the screen. And if you look at a standard arcade kind of game, in terms of graphics, there isn't much more than this, right? So I don't know. I've been talking for what? What time is it? 15 minutes, and we already have all the machinery we need to create a really basic drawing on the screen and maybe a basic game, right? Oh, okay. Any questions, comments so far? Anyone? Anything that you don't understand? Yeah, all the code is there. So, yeah. Let me see if I can get. So, STL pointer animation. So, animation frames, for instance. Let me see if I can run this. So now, for instance, let's see how we can run, how we can animate something as basic as this, right? And this is really simple. It's really stupid. I feel stupid talking about this, but when you add animations, like frame-based animations like this, it's a whole new dimension for a game, right? So it's just this simple. I think it was animation scrub. Wait. Animation frame. Oh, yeah. tutorials, game concepts, multimedia, animation, main. So what I'm doing here is I'm loading a bunch of frames from a file. It doesn't have to be implemented in this way, but the idea is that I'm going to show different images at different times. And you can do that in two ways. You can either load different images, and at different times you actually show different surfaces, or you load one surface with all the images, and then you just select different areas that you paint on the screen. It used to be done that way, because loading textures took a long time, and it was easier to load everything once and then just select different areas. So this is what it looks like if you go to the GitHub repository. I think it's Flapping Bird sprites. These are all the images, and well, what it generates you have already seen, right? It's just that. So what it's doing is it's loading the file path in a surface. That's a standard SDL call that gets you a surface with all the pixels in the image, and then it's creating. You don't have to use this particular type if you don't want to, but the idea is that you have a list of coordinates on the screen for each frame. So if for the first frame you have these coordinates, for the second frame you have these other coordinates, and so on. And at some point when you render, you just render different areas. And how you render different areas is like this. If you have a sprite animation with a surface and an area, a rectangle, well, this are all the coordinates. You select based on the frame, and then you just render that particular rectangle. So when you blit, you can either blit the whole surface on top of another, or select an area using a rectangle, and then just split that one. Is this understood? Okay. I guess nothing means yes. Let me see where we are. So far we could already. Let me see. So one of the things that I like to do is I like to use other kinds of hardware to interact with from Haskell, and I use Wiimotes a lot. They use Bluetooth to communicate to the machine, and they just tend to work out of the box. I'm going to try an example, see if it runs fine, and let's build Wiimote IRLets. So how a Wiimote works is that oh, wait. Okay. This has nothing to do with Wiimote itself. It's just both GAC and the Wiimote library uses the same signal for something, and you need to compile it in a special way. But okay, so hopefully that will be enough. Oh. Okay, Bluetooth here. Let's see if it works. Come on, don't let me down. Okay. So what you see is that it's printing, it's pulling the Wiimote really, really fast, and it's printing a dot if there are no buttons pressed, and something like a hash symbol if I press this button. And it's printing one hash per time it pulls the Wiimote. So it's pulling really fast. Right? That's not impressive. No, it's not impressive. Save your applause. Oh, someone is trying to connect to. Yeah. let's see if I can, oh, point. No, let's is better. Higher, let's. So I try to connect. And if I did everything right, come on. Yeah, okay, cool. If I did everything right, you should be able to see this now. So what you're seeing is that there's an infrared camera here, and it detects two LEDs, well, it's actually four LEDs, but two LED infrared sources sitting on each side of this bar. So yeah, so when I do this, it's in, I'm covering this. There's a few LEDs on each side, but when you get too far away, it's just one source for each side. Okay, wait. Yeah, okay. This is just a circle using SDL, as we saw before, painted on the screen with a fixed size. And if you get far away enough, you see that it's really fast. I mean, it's not, Haskell is not getting in the way of using something like this. Now I'm going to show you the code, and I think you're going to laugh at how simple it is. Tutorials, hardware, Wiimote, tutorial 3, LEDs. The library is here, is this one. It's also on GitHub, and we maintain it. And you connect to the Wiimote. Initially, you have to press these two buttons at once to connect to the computer. And once you actually get a Wiimote, a handler, all you have to do is set the reception mode, like tell the Wiimote what you're enabling and disabling, and start getting data. And with this, you get all the infrared sources, and you get positions, sizes, how big it is from that perspective, and I think you don't get anything else. And here you're painting them. So this is just a list of infrared sources, and with these two functions, which are in the library, you get the coordinates. And that's what you're seeing on the screen. Of course, if you want to write a game, you don't want to see two coordinates. You want to see just one to control one player. So that's also easy to do. And I think we can point, yeah. So if I connect to this one, let's see if it works. Cool. Okay, so now this is better. And if you calibrate it right, which is not, but if you calibrate it right, you could actually point to the screen. And I even brought one thing that people used to use sometimes to do this. Where is it? Oh, yeah. You can use this if you want. And put your Wiimote here. And close it. And use it like this to play games. Right? This is, calibrating this properly is just standard geometry. It's just a perspective transformation. There's nothing special about it. And you can read about this in any 3D or 2D book. Yeah? Okay, so the library doesn't do it for you, but I wouldn't do it in SDL. SDL is only used here for rendering. It's not used for any kind of perspective transformation. So you would have to do it in Haskell. Sorry, what? No, that's the point. That's the point. You don't need to know the distance from the screen. When you calibrate, you don't need to know it. There's a really good source of information for anything that has to do with the Wii, which is, I think is Johnny Lee is his name. He created like a whiteboard using a Wiimote. Instead of using the Wiimote to point to things, he placed the Wiimote looking at the screen and then used the pen with an infrared LED on the tip to draw on the screen. And at the beginning of his program is open source, and at the beginning you calibrate it. 4 crosses at the beginning, and you have to to take your lead and put it on the cross to give 4 coordinates, and then that's how it applies the matrix transformation. If you have 2 of these, you can also do that. So, for instance, if you have to, so what you said, who said about the needing to know the distance? I think it was you, right? You're not going to have like a 3D coordinate in space unless you know that, I mean, from only 2 sources of infrared. You would need 4 sources. This can track 4 points, so if you have 2 wee bars, you actually have the distance. As long as you know how much they're separated, you have a 3D coordinate in space. Okay, cool. So so far we know how to, yeah. The chip that's processing for you, and so the Wiimote has a, I think it's like a 144 times 96 pixel camera. So it's really small resolution, and there's a chip that does object tracking for you. That's on the Wiimote itself. No, not for the Wiimote. It's a pity, but it does really good object tracking, as you saw. I mean, this kind of object tracking from what, 5 meters is coming from a 144 times 96 pixel camera. So that's really impressive, I think. The object tracking is really good. But of course, it would be nice to at least be able to see what the camera sees. Charging the cable, if you have a Wii, you will see that you have a cable that goes from the bar onto the Wii, and that's only to charge to turn the LEDs on. There's nothing special about the bar. The bar is only a point of reference. It sits on top of your television, and that's the only thing it does. Right now it has a battery, but this is not an original Wii bar. If you buy the Wii, then it doesn't have a battery. It just has a cable, and then you plug it to the Wii with a proprietary adapter thing that Nintendo has. Probably yes. So you can use candles. You can use any source of infrared light. So when I try this on rooms that are very well lit, I get interference from the sun, from the outside. Cool. Okay, so I have a third remote if you want to borrow it, and you can get candles somewhere outside. Okay, so far we already have all we need to run this example, right? Let me see, raindrops. So with what you have seen, you should be able to run. Oh, wait. Yeah, okay. Okay, cool. So if I do this, okay, so I just need to do this and say options. Cool. What are you talking about? Yeah, I did it. What's wrong? Okay, I don't know what's wrong. I don't know why it doesn't work, but example, raindrops. Oh yeah, samples, raindrops. Cool, cool, cool. So now we have this. Come on, don't let me down, huh? Okay, cool. Anybody wants to play? You have to catch those things. We already have enough to create something like this in 30 minutes of Haskell. And of course, it's not going to, I don't know, they just go faster as you move forward in the levels. As you get more and more, then they go faster. So we're using Wiimote and SDL to create a game that is not incredibly amazing, but it's actually a lot better than what you see on the papers and what most people show you when they talk about game programming in Haskell. And the code for this is online. The only difference between what I showed so far and this is that it's doing collision detection. And it's just seeing if the paddle, this thing that I'm moving, overlaps with these fruits that are falling. But everything else you already saw. Okay. Sorry? I think this, oh no, it's not taking the shape from the PNG file. That's really complex. So physics is an extremely complex problem. And it really is affected. So the problem in physics, one of them is whether you can actually detect what you want to detect, and the other is how fast you can do it. And it's completely affected by the kind of shapes that you have and the kind of movements that you have. So in a game like this, for instance, I think it's only using squares, so it's assuming that those are square, and that makes the whole problem really easy. The easiest way to do it is with circles, actually, because then detecting overlapping is just checking if the distance between the centers is greater than the sum of the radii, and that's it. But so there's two sub-problems in physics. One of them is detecting whether things overlap, and the other is solving the situation when things overlap. The second one is actually the hardest one, in my opinion. I'm not an expert here, but I think it's the hardest one. Because if you think about it, detecting whether things overlap gets complicated only if you have something like concave shapes, right? Imagine, for instance, that you have a ball going this way, and then you have a concave shape going this way, and it's rotating. And the ball goes this way, and it does something like this, and it keeps going forward. If this were convex, then they would just, at some point, touch each other. And you can detect when that's going to happen, because you can see the movement of this one, the movement of this one, and see that at some point the paths are going to cross. You draw rectangles, you see that there's an overlap, and you see when you know when it's going to happen. But if it's rotating, the trajectories might overlap, and there's no collision at all. And it's really hard to know that there's going to be no collision at all. That's the hardest problem in collision detection. Now, solving the collision, that's even worse. Solving the collision means, for instance, that imagine that I'm running towards the wall. I'm one of the characters. I'm running towards the wall. You sample here. There's no collision. And then you sample when I'm already into the wall. How do you solve it? Well, the wall is not going to move, so you have to move me out. That's usually how it works. So you just separate things. And when you separate things, there might be another object here. So you also have to push that one out. And depending on how many objects there are and how much space you have, you might have too many things. And then it's really hard to simulate that and get to a point of equilibrium. And there's two ways of doing physics. One of them is you just simulate the physics at specific times and see what happens. The other is you know ahead when something is going to happen. So for instance, if I'm moving towards the wall and you know my speed, you can calculate when something is going to happen. And that's it's called time of impact detection. The idea is that you know when something will happen, and then you simulate that step, and then you solve that situation there. We'll talk more about physics when I talk about FRP. Okay, cool. And before the break, I think I'm going to show you if I can get this working. Yeah, a little bit of Wiimote. So a Wiimote, a Kinect. You know what the Kinect is, all of you? So Kinect project a matrix of infrared points, and they analyze how the points are deformed in space to try to guess the distance to different elements on the screen. So essentially, it sees in 3D. So if I get this plugged and running, yeah, we might be able to see something. This is really buggy, by the way. It's not. Okay, I'm not sure it's working. If it doesn't, please forgive me. The code is still online, but this is really buggy. So Kinect pointer might work. Does it? No, I think it's not working. Right. Well, it's rendering at 800 frames per second, so it's definitely not working. No, the calculation is correct. It's just not doing the Kinect image processing. Definitely not. Well, if you have a Kinect, there's an example online. There's a game online that you can use to try this. Oh, come on. Sometimes it's, nah. Okay. I'll try it later again. During the break, I'll see if I can get it working. But the idea is that, no. It used to be. This kind of device can essentially see you in 3D. On Linux, it doesn't do any kind of skeleton analysis, so it doesn't know about your limbs and stuff. It doesn't do as much as it does on Windows or an Xbox. But at least it can tell you the distance to different points in the image. And you can use that to, just interact with the game. So there's a game online called Haskell, which is an implementation of Arkanoid in Haskell. And you can play that with this kind of device. And it's actually fun. I mean, if you have one of those, I really recommend it, because you have to run across the room to play, and it's hard. It is hard. I was thinking of talking about higher level problems now, but I don't know if you prefer to take the break now, or if you just want to can go on and then take the break in the middle of the second half of the talk. Okay, I don't know. I'll just keep talking then and give you a preview for those of you who are wondering whether you should go to the other room, me included. So the only important things about SDL that you need to keep in mind, apart from, well, you have to initialize the library, SDL does keep structures in memory for you, and that means you can't free them. And that is actually annoying, because Haskell has a garbage collector that will try and free things for you. And if you're playing a sound or showing an image, it tends to lead to some really nasty bugs in which you don't know what the hell is going on. So if you free surfaces, for instance, if you load a PNG file and then you free it, you stop using it, you have to make sure that it's no longer being used anywhere. That is more relevant for audio, for instance, because audio is played asynchronously in SDL. So something may still be played, and you stop having any pointers to it. You stop keeping that in any data structure, but it's still being played. If you remove it, then the sound will stop all of a sudden. Sometimes at the beginning, for instance, I had examples where nothing was being played, and I didn't understand why. And it was because I wasn't keeping a handle. I wasn't referring to that specific C structure from any part of my Haskell code. Those are the kind of things that you have to think about when you use SDL from Haskell. What else? It works. So there's an event queue. Oh, I didn't talk about. Wait. Great. I didn't talk about input in SDL. I talked about this and not about input. So if how input works in SDL is that you have an event queue. Yeah, cool. Okay, so there's an action that gives you the next event that has been accumulated in the event queue. So if the mouse is moved, if you click, anything that has to do with input will be accumulated in a queue for you, and then you just pull events from there. You keep pulling until you get to no event. And when you get to no event, you know that you have consumed the whole queue. So how it's working is that at every game loop iteration, you just consume the whole event queue, process that in the game, render on the screen, and then go on again. And for instance, this is I don't know what this example does, but essentially, yeah, okay, there's a controller that has a gun that may be firing or not, and then some position on the screen, which is the position of the mouse. That's for the game that we saw, the one with the bar that moved. And you can also control it with the mouse. And when the mouse button goes up, the left mouse button goes up, then the gun is no longer firing. So this is updating a Haskell structure, processing the events from the SDL queue. Yeah? On Android, it will also give you information about, well, it gives you information about when a window is resized and things like that. And on Android, it also gives you information about your activity dying. So how Android works is that you have activities, and activities have lifetimes, and they can be paused, they can be stopped, or they can just be killed almost all of a sudden. And those come in as SDL events as well. I think.
So what does the typical event look like? So this was the one part, but where's the other part where you...
So raindrops, I think, examples. Raindrops. So this is the game that you saw, the one with the things falling, the cherries falling from the sky. This loads all the resources that it's going to need and connects to the Wiimote. And this is how it works. Okay, so first you sense you detect the paddle position. That's going to consume either SDL or some sort of events or pull the Wiimote, and then you process it. You process the physics, detect collisions. These are pure Haskell calculations, and then you just render. Okay, so every simple game is going to work like this. You have a game loop, and you have three actions: sensing, processing things forward, like moving things forward, and then rendering on the screen. And it always goes like this. In more complex games, you cannot do this, or if you don't have a fast CPU, you can't do this. But for simple examples, it works well. For board games, it works well. And I even use it for more complex games when I want to just test a specific feature. Okay. Does that answer your question? Yeah?
In more complex games, you don't use it?
It's not that they don't use it. There is a game loop, but it's desynchronized. So one thing that happens with game loops is that it's synchronous. You sense once, you render one, you process once, and then you render once. And what happens is that the renderer is going to probably run at 60 frames per second. But your physics, to look realistic, has to run a lot faster than that. So on a game like Breakout, if you don't run at least 70 or 80 frames per second, you see that the ball goes in between, blocks and bricks, or it goes into the wall a little bit. And so you need to run the physics faster. So one way to do that is to add mvars or some sort of mechanism in the way. We'll talk about that later. But just run things in different threads and have them communicate. Other people, what they do is they run the physics twice per cycle, and then they just adjust things. But I prefer to just separate things in different threads. Also, this thing can be pulled really fast as well, a lot faster than render and the physics. Not that you might want to use that if you're not going to simulate physics, but some devices, for instance, a webcam, can only be pulled at 25 frames per second, possibly. So you don't want to be pulling the webcam all the time. Or wait for it. I think is it time for the break? Or what time is the break? Yeah, it's time for the break. So if you want to have coffee or something, go ahead. We'll be back in 15 minutes. If you want to go to the other room, I will hate you forever, but don't feel guilty. In the second part, we'll talk about functional reactive programming, see examples of games on Android, on Linux, and get pointers to resources that you can use online, see other games that people have implemented